Hi everybody, we're going to have a look at June 2015, Unit 4, Section B, Question 2. So it's about electric fields, and it's one that some people have struggled with in recent mocks. So, Part 2a says, state in words Coulomb's law. So, we know that Coulomb's law says force equals so let's call it Q1 and Q2 multiplied together over 4 pi epsilon naught r squared. So if we've got two charges, Q1 separated by a distance r from Q2, and the force between those two charges is Q1 multiplied by Q2, all divided by 4 times pi times epsilon naught times r squared. So what we can do is, if we take out all of the constants, there's a constant in front, so it looks like F equals K is a constant, Q1 Q2 over r squared, or force is proportional to Q1 Q2 all over r squared. So in words, that says that the force between two charges, we should go up here, so the force between two charges is proportional to the product of the two charges. So that's Q1 multiplied by Q2, so it's proportional to the product of the two charges, and inversely proportional to, so in words, it's the square of their separation. When we talk about inversely proportional to, we mean that the force is proportional to 1 over r squared. In this case it's 1 over r squared. So inverse proportion is proportional to 1 over something. Okay, let's take a look at 2b. So it says, state what can be deduced from the graph about how v depends on r and explain why all the values of v on the graph are negative. So the first thing we're going to look at is, we'll look at our line. So it's a straight line. So that means that the y value is proportional to the x value. So in this case, v is proportional to 1 over r. Okay, so that's our relationship between v and r. So the potential, the electric potential, is proportional to, or inversely proportional to, the radius. So why are all the values negative? So the simple answer is that Q is negative. So that's our simple answer for our second point. You get both marks for saying that. Why is it that if Q is negative, our electric potential is negative? So if you think about our definition for electric potential, so V is the work done in moving a small positive test charge. So it's small so that it doesn't interfere with the field that we're testing, and it's positive by convention. So electric potential is the work done in moving a small positive test charge from infinity to whatever point we're talking about. Okay. Okay, if we're talking about a negative charge rather than a positive charge, if I have to do work to move a positive charge, then I'm going towards a positive charge. Or in this case, we've got a negative charge, haven't we? So if we take a small positive test charge and we put that positive test charge near our negative charge, then we don't have to do any work to move it. The field actually does work. Okay, so we get negative work done. We get some energy back, if you like. That's the long answer, but your short answer is up there. So that's your 2 points. Okie doke. So 2CI. So it says use data from the graph. So we'll keep the graph in view. Use data from the graph in figure 3 to show that the magnitude of Q is about 30 nanocoulombs. So what do we know? So we know the electric potential. We can find R, the radius, or the distance between the point we're talking about, which can be any of these points, and the charge that we're looking for to make magnitude 30 newtons. So if we find, just get rid of that one. So if we find our equation for V, our electric potential is Q over 4 pi epsilon naught R. Now we don't want V, we won't want potential, we know potential, we want Q. So actually Q equals my electric potential times by 4 times by pi times by epsilon naught. So that's a permittivity of free space. It's 8.85 times 10 to the minus 12 farads per meter, and that's should be in your data book. And we're going to multiply that by R as well. So we can read off the graph. We can read off, find a nice easy one. So we'll go from 100 across to, that's not a very straight line, is it? Let's try this. We'll go from 1,000 across to 4 and then up. So we can read off 4, but that 4 is actually 1 over R. Okay? So in order to find R, we're going to do Q equals, so it's minus 1,000 times by 4 times by pi times by epsilon naught, which is 8.85 times 10 to the minus 12. Now we're going to times that by R, which is going to be 1 over R, which is 4, so power minus 1. So we take the reciprocal of the value of our x-axis, and that will give us what we want for the value of R. So if you pop all that into your calculator, you'll find that Q equals 2.78 times 10 to the power minus 8 coulombs. So we can convert that and we can say that it's 28. So it'll be 28 times 10 to the minus 9. If we make that once bigger, we have to make this once smaller. So that's 28 nanocoulombs. And 28 nanocoulombs is about 30 nanocoulombs, which you don't have to write that you've already shown that 28 nanocoulombs is about 30 nanocoulombs. Okie doke. 2CII. So a 60 nanocoulomb charge, positive 60 nanocoulomb charge, is moved from a point where R equals 0.2 to a point where R equals 0.5. So calculate the work done. Now we need an equation for this. We know that the work done is equal to the product of the charge and the change in potential, or the potential difference from moving from one point to the other. So what we want to know is where R equals 0.20 meters, 1 over R equals 5, that's meters to the minus 1. And we'll go back up to the graph in a second. So we're going from here, so R1, 2 here. So that's 0.50 meters. So 1 over that is 2 meters to the minus 1. So if we have a quick pop back up to our graph, we're looking for 5 and 2. So 5 is halfway between here and here. So we'll go, ooh, I've missed. No, I'm not sure I have. So it's 1, 2, 3, 4, 5. Down to there. And across to there. So that's halfway between 1,000, 1,500, and then 2. It's easier for me to grab. That's 500. So where we've got that's minus 500 and minus 1,250. So where we had 5, then V equals minus 1250 volts, and then where it was 2, it was minus 500 volts. So looking back at our equation, our work done is 60 times 10 to the minus 9 coulombs, which is our charge that's given in the question, multiplied by the difference in potential. So it's our final, which is minus 500 volts, minus 12. So difference is the final minus the initial, and our initial was minus 1250. Pop that into your calculator, and you should get a value of 4.5 times 10 to the minus 5 joules. What I recommend, just leave that as it is. You're not going to lose any marks for leaving it in standard form. The final part says, calculate the electric field strength at the point where R equals 0.4 meters. So we need an equation for electric field strength, which is Q over 4 pi epsilon naught R squared this time. Now, our electric field strength is due to the charge that we found earlier. So it's 28 times 10 to the power minus 9 coulombs, all over 4 times pi times 8.85 times 10 to the power minus 12 multiplied by 0.4 squared, which is fairly straightforward to type into your calculator. Gives us an electric field strength of 1574 volts per meter. We don't want to leave it like that. It's 4 significant figures. We've got 2 here, which is likely to be our smallest, so we'll go for 1600 volts per meter. And that takes us all the way to the end of that question. Now, I hope that's been really useful. If you've got any more questions, leave them in the comments below. If you've got any questions about any other parts of this paper or any other paper, put them in the comments and I'll see if I can do a short video to help you out. Thanks very much.